So in this video, we're going to take a look at the idea of spontaneity, pull in some of those other measures of spontaneity that we've learned about in the past, KEQ as well as Gibbs free energy, and we're going to relate that to the EMF, the electromotive force of a galvanic cell. So let's develop the mathematical relationship between those two. So one of the new equations is that the change in Gibbs free energy is equal to negative NF and E of the cell. Okay, so what are all these things? N is the number of electrons, so it matters how many electrons are moving. Do we have 2 electrons moving? Do we have 10 electrons moving? F is Faraday's constant. It is actually the quantity of electrical charge in 1 mole of electrons. Faraday's constant is a constant, so it is 96,485, or a lot of times they'll just use 96,500 coulombs per mole, or if you remember, the coulomb helped us relate back to volts and joules, so it can also be expressed as joules per volt mole. So keep these units in mind. We're getting into, in the next couple days, we're getting into some units that are brand new to you. So keep these conversions in mind. And then obviously, E is the voltage of the cell. So a positive voltage winds up with this negative sign here, winds up giving you a negative delta G, which supports spontaneity. A negative voltage for the cell means delta G is not spontaneous because delta G winds up being positive. So there's the relationship between those two. We can also get equilibrium into the act. So when a reaction takes place under standard conditions, you have delta G naught equals E cell naught. But again, we can also relate the delta G naught to the equilibrium constant. In this way, if you remember, we saw this reaction before. Delta G is equal to negative RT ln of the equilibrium constant. And so we can set all 3 of these things equal to each other. So another way to directly relate the energy, the voltage of the cell with the equilibrium expression is to make these 2 substitutions with all of these constants, R and F, and T, because we're talking 298 Kelvin. So notice how all the units cancel out appropriately except for the volt. So we wind up with E naught of the cell is equal to 0.0257. That's mathematically what you come up with, divided by N, and remember that N is the number of electrons, ln of K. And if you want to use log, the voltage becomes 0.0592. So either one of these works. You can use whichever you prefer. They should work out the same way. Okay, so here's kind of a nice visual to let you see how everything relates to each other. Delta G is equal to negative NF E naught of the cell. Delta G is equal to negative RT ln of K. And then the E naught of the cell combines all of those constants to equal the natural log of the equilibrium expression. So remember, depending upon what you use here, log or natural log, this number is going to change slightly. So just kind of as a review in terms of what values are we looking for something to be spontaneous. For delta G to be spontaneous, meaning we're going to favor the products, we're going to have the reaction go. You want a negative delta G, you want KEQ to be greater than 1, you want the denominator to be, or the numerator to be favored over the denominator, the products to be favored over the reactants. You want the voltage of the cell to be positive. At equilibrium, delta G and E naught of the cell will be 0, and the equilibrium expression will equal 1. And then if the reactants are favored, if it favors the left side of the reaction, delta G will be positive, KEQ will be less than 1, and the energy voltage of the cell will be negative. So keep these ideas in mind in terms of what supports spontaneity and what does not. So let's do some examples. So we've got this chemical reaction, iron ions reacting with silver metal and going to iron metal and silver ions. What is the equilibrium constant for this reaction? Well, we're going to start off figuring out what the voltage of the cell is, because we can do that. To get this guy, we're going to figure out this guy first. So oxidation, we know, is going to be silver going to silver ions. Reduction is iron ions going to iron. We can get, well, we've got 2 electrons there, so we're good there. Total of 2 electrons involved. If we get the voltage, we pull these right off the reduction potential sheet. We know that for reduction, it's a negative 0.44. For silver reduction, it's a positive 0.8, but we're going to flip it, so we're going to make it a negative. So overall, the voltage is a negative 1.24, so it does not favor this reaction to happen. Silver never wants to become silver ion. But what's the equilibrium expression, or the equilibrium constant, going to be? Rearranging this equation and solving for K, we find out that K is 1.23 times 10 to the negative 42. Very, very small number means that the equilibrium constant is telling you that the reactants are being favored. So that supports that the voltage not being spontaneous as well. The effective concentration on cell EMF is also something that we want to take a look at. So to look at concentration, we're looking at not at K, but we're looking at Q. So we're going to go back and use the delta G equation when you are at non-standard conditions. This guy also comes into play. And then, so for standard conditions, delta G equals negative NF E naught. So we're going to substitute this for that, this for that, in order to figure out how concentration is going to affect things. This is referred to as the Nernst equation. And so we can get rid of the constants, or move the constants around, divide everything by NF, we get RT over NF, make these positive, which means that guy becomes negative. We've got E equals E naught minus RT over NF, ln of Q. Again, we're just deriving all of these things, but this is what's referred to as the Nernst equation. The Nernst equation lets us measure the effective concentration on the cells. So at 298, this is the value that we've got, which is our standard temperature that we're worried about, 25 degrees Celsius. Or you can do the log version. And so here is an example. Will the following reaction occur spontaneously at 25 degrees? So we've got concentrations of solutions. We know that cadmium is being oxidized. We know that iron ions are being reduced. 2 electrons is what's moving. Let's get the voltage of the cells. The reduction for iron is negative 0.44. The reduction for cadmium is negative 0.40, but we've got to flip that sign. So we have a voltage that's a negative 0.04 volts. That's really bad for spontaneity, right? So that's what our value is here. But let's figure out Q based on these concentrations and see what the overall voltage is going to be. So we've got, I guess I should have put in an intermediate equation here. To Q, remember that it's products divided by reactants. Well, CD2 plus is our product, so that's why the 0.010 is on top. Iron ions are on the reactant side, so the 0.6 is on the bottom. So that's why these numbers are where they are, because of how Q gets expressed. So we solve for a voltage that now, in this case, is positive. So even though under standard conditions this would not go, because I have such a high concentration on the reactant side, it actually does drive it to have that reaction work. So this is going to be positive, or this is going to be a spontaneous reaction, even though under standard conditions you wouldn't expect it to work. Under non-standard conditions, very high concentration for the reactant, very low concentration for the product, you're going to see it being driven towards the product side. So then the one other idea that we can take a look at is, what if we have two substances of the same material, but with different concentrations in the different cells? So you're actually going to do a lab with part of this as one of the ideas. So does it make sense that the high concentration of zinc is going to try and move towards the lower concentration of zinc in the opposite half cell? So you always have the higher concentration being used up. So to use up the ions, you want to have that undergo reduction. And then the lower concentration, to try and make that concentration higher, you want to create more ions. So this side you're going to have undergo oxidation. So reduction for the high concentration one, oxidation for the low concentration one. So the net reaction, therefore, is going to be zinc 2 plus going to zinc 2 plus, but having different concentration. So the voltage of the cell is 0. We've got nothing in terms of, or at least for standard voltage, it's going to be 0 because we're dealing with the same thing. But because the concentrations are different, we are going to get some voltage. So if we stick our numbers into the equation, we wind up with a voltage that is positive. It's going to happen because it's going to try and reduce this concentration, try and raise that concentration until you get to a point where when the concentrations are equal, then the overall voltage is going to be 0 because you'll have natural log of 1, which is 0. All right, so there's the Nernst equation. We're going to do some work with that, some practice with that, but at least you've seen the basics. So keep in mind you've got those 3 interchangeable, not interchangeable, but 3 reactions that are related to each other that let you get back and forth between the 3 ideas that push the idea of spontaneity. So those are some pretty important reactions to be comfortable with.